Hello, today I'm going to review for the AP Chemistry exam by going over the 2023 released free response. Question 1 is a long free response. These are worth 10 points each. So manganese has 25 total electrons, so if we rate the complete electron configuration, we start at 1s, 1s2, and then 2s2, 2p6, 3s2, 3p6, then when we get into the next row, 4s2 and 3d5 to get to those 25 electrons for the ground state for manganese. Now, when it forms cations, electrons are lost from which subshell. Because it's a transition metal, it's going to steal the electrons from the 4s sublevel first. Those are the outermost valence electrons, so we'll lose those. So you would say 4s. Identify both the number and the letter, so 4s. Okay, we're going to do an experiment to find the empirical formula of a manganese chloride salt. We have manganese in a beaker reacting with hydrochloric acid. Heats the mixture until only the MnCl remains in the beaker because the hydrogen gas is going to evaporate at higher temperatures, or which is vaporize, might be a better word. The data are given in the following table. Okay. Calculate the mass of the chlorine in the sample remaining in the beaker. I would take the final mass there, the 62.673, and subtract out the 61.262 grams because we want to find just the chlorine. So we want to get rid of the beaker and the manganese. So when we subtract, we get a 1.411 grams of chlorine. Now, this one might have been a sig figs question, so you want to make sure that you're using all of the decimal places that were given when you're subtracting there. Okay, so now we're going to use the mass we just calculated, the 1.411 grams, and find the moles now. We need to use the molar mass of chlorine, which is 35.5 grams per mole, and when you calculate, you get 0.03980 moles of chlorine. Now this might have also been a sig figs question for sig figs here. It was either this one or B was the sig figs question, but one or the other. So please make sure that you're consistent with your sig figs. Then the student determines that we have 0.0199 moles of manganese. Use the data to determine the empirical formula. So 0.0199 for manganese and 0.03980 for chlorine. You just divide by whichever one's smaller, which is the manganese. And so we get it is a 1:2 ratio there. And so the empirical formula was MnCl2. Okay, so the student repeats the experiment using the same amounts, notices that some of the product splatters out of the beaker as it's heated. Will the number of moles of chlorine calculated be greater than, less than, or equal to the number calculated in part C? It should be less than. So imagine you had your original mass of just the beaker, and the Mn was 61.262 was the beaker and just the manganese, and then our final mass in the data table was 62.673 grams, and we subtracted to find the 1.411 grams. So if it's saying if some of it splattered out, then this mass here would be smaller. So there would be a smaller difference in mass. And then when you went ahead and calculated the moles of the chlorine, that would be smaller as well. So really make sure that when you're asked questions like this, that you follow the math through from the where the measurement will actually change all the way through the calculated part that it's asking you about. So if we have less than the number of moles, then you calculated in part C. Okay, so we have MnO2 used in alkaline batteries represented by the following diagram. So this picture doesn't really affect your answers for this question, but it's a battery, right? So it's an electrochemical cell. It's just not drawn how we usually see it, but hopefully it shouldn't have affected any of your answers. Now, for part I, we want to write the balanced ionic equation for the reaction that has the greatest thermodynamic favorability. So that means that we're looking for the most negative delta G or the most positive cell potential. So knowing that we're looking for the most positive cell potential, we want to take these half reactions and try different combinations until we find the value that gives us the most positive cell potential. And that will happen is if we flip this reaction here and get the zinc plus the 2 hydroxide, flip it to zinc oxide plus water plus 2 electrons. When we flip it, it changes to positive 1.28. And I'm going to combine that with the final reaction here, the 2MnO2 plus water plus 2 electrons yields the Mn2O3 plus 2 hydroxides. And that one is 0.15. Now, when you're finding the overall Net Ionic Equation there, you want to cancel out anything that is the same on both sides and make sure that the electrons are the same. So our electrons cancel, they're the same, that's all good. I have a water on both sides, so that's good. And my 2 hydroxides also cancel out. So I'm left with the zinc metal and the 2MnO2 on the reactant side, and zinc oxide plus Mn2, excuse me, Mn2O3 on the product side, just like that. Now you should include your states, and actually all of these are solid, like that. And so that is the answer for part I. Now you're just a very short step away for part II. You just need to actually add those two together to give you that most positive value for E cell, which is positive 1.43. Okay, so now we need to find the value of delta G. So we can use the equation delta G equals negative NFE. And we just, when our balanced equation, we found that there were 2 electrons. So I know N is 2. Faraday's constant 96,485. And our standard cell potential that we calculated in part II was 1.43. So when you multiply those together, you get negative 276,000 joules, because the equation there will give you joules. But the question's asking for it in kilojoules, so you just need to convert that, divide by 1,000, and you get your final answer is delta G equals negative 276 kilojoules per mole. Okay. Then for part IV, student claims that the total mass of an alkaline battery decreases as the battery operates because the anode loses mass. Do you agree with the student's claims and justify? You should definitely disagree. So if we look again at your balanced overall reaction, all of the reactants and products are aqueous or solid, even if you're looking at before the Net Ionic Equation, right? You want to look at the overall reactions for the anode and the cathode. Nothing there is a gas. Okay. Sometimes when you have reactions like this, it produces a gas, and the gas escapes into the environment, so the mass itself decreases. But because it's all contained together and they're all aqueous or solid, there's no overall change in mass. And if there was, it would violate the law of conservation of mass. So you'd say you disagree because all of the reactants and products are aqueous or solids, so they do not leave that contained battery. Question 2 is the second long free response question. So this is a stoichiometry question. First, we have how many grams of chloride can be, or chlorine can be formed from 1.25 moles of aluminum chloride. And we know that there's 1 aluminum chloride in the balanced reaction for every 3 chlorine atoms. And we want to find grams, so we need to use the molar mass of chlorine. And when you solve that out, you get 133 with 3 sig figs grams of chlorine. Now for B, they give us these additional reactions. So we have reaction 1 from the first part, and then we have reactions 2, 3, and 4. And they want us to calculate the value for reaction 1 using these above reactions. So effectively, this is a Hess'S Law. We're looking for a combination of these reactions that will add up to this overall goal reaction. So what I need to do is I need to flip this first, or reaction 2, I need to flip that around. So I get the aluminum chloride on the correct side. And that will change this value to a positive value. And this is our solid aluminum and gaseous chlorine like that. I also then need to flip this reaction around so I get the, no, I don't need to flip it, I'm sorry. I do need to use it though. I have the solid aluminum going to aluminum gas. But that way the solid aluminums are going to cancel. So, but that one stays as is because I didn't have to flip it. Now for the last one, I need to go ahead and multiply this reaction because we have 3 chlorines on the product side, but this reaction has only 2 chlorines. So I need to multiply this whole thing by 1.5, and I'll multiply the reaction by 1.5, or by 3 halves. So 3 halves chlorine gas yields 3 chlorides, and that way the 3 halves of chlorine can cancel as well, and you're left with your correct overall balanced equation, which we have at the top here. So now when you're solving for the value of delta H, you would do the positive 583 plus 326 plus 1.5 times the positive 243. And that gives us a value which is rather large, 1274 kilojoules per mole for that reaction. And it is positive, of course. Okay, so we have this potential energy diagram. What is the bond length in picometers? So you always want to look at the lowest potential energy, so it's here, and that's at 200 picometers. That's it. But for part II, a student finds that the average aluminum to chlorine length is 220 picometers. Okay, so that's here, right, 220. And then the average bond energy is 425. Now, bond energies are typically given as positive values, but then their potential energy are given as negative values. So we're going to be looking at a 220 distance, but a negative 425 is our potential energy because it needs a negative value. So then, as long as you got that bottom part in the correct spot, if your graph isn't as, pretty as the original, that's okay. But it does need to try to touch that point. Let me use a different color, see if it stands out better. Like that. Now for part D, we've got 3 Lewis diagrams, and I wants us to, well, it tells us that AlCl3 has a trigonal planar. Now, which diagram can be eliminated based on the geometry? And that's going to be diagram 2 can be eliminated. And that's because when it has 3 bonds and a lone pair, that's trigonal pyramidal Hbr geometry, which is not trigonal planar. So that helps you to eliminate that one. And then for part II, which of the 3 diagrams is the best representation for the bonding in AlCl3? Hopefully you didn't pick 2 because you just eliminated it. But let's look at the formal charges. Formal charges is always the normal electrons, normal valence electrons, minus the electrons that are currently assigned to it. So aluminum normally has 3, And in diagram 1, it has 3 bonds. So 3 over 3 is 0 for that aluminum. Chlorine normally has 7 valence electrons. And each chlorine has 6 lone pairs and a bond, so that's 7 assigned to it. So those are also 0. It's looking like diagram 1 because we want all of them to be 0, but let's check diagram 3 really quick. Aluminum normally has 3. Right now it has 4 electrons assigned to it from those 4 bonds. These chlorines have 7 normally and 7 assigned to them. And this last chlorine normally has 7, but right now it has 4 in the lone pair electrons and 2 bonds. So 4 plus 2 is 6. So that's a positive 1. So diagram 1 is the best representation because all of its atoms have 0 formal charges, whereas diagram 3 does not have formal charges. Okay, so the Kp expression for this, it's always products over reactants, so pressure of Al2Cl6 on the top, and then we have our AlCl3 squared on the bottom. And then they give us a particle level diagram of an equilibrium mixture at 400 degrees Celsius in a 25-liter closed container. Calculate the value of Kp for the reaction if the total pressure is 22.1. Okay, so in this container I have 3 particles of the Al2Cl6 and 7 particles of the AlCl3. So that means I have 10 total. So 3 out of 10 of my particles are the Al2Cl6, and if my total pressure is 22.1, that will help me find the partial pressure of the Al2Cl6, which is 6.63. And then 7 out of 10 of my molecules are AlCl3, which is, if I multiply by the total pressure of 22.1, I get the partial pressure is 15.47. And then finally, I can plug that into my Kp expression, the 6.63 from the Al2Cl6 on the top, and the 15.47 squared on the bottom, and I can find my Kp value is 0.0277. Question 3, this is the last of the long free response questions. Okay, so for net ionic equation for this one, we can, anything that is completely aqueous on both sides can be eliminated as a spectator end, and in this case it's just the chlorine ions, so we're left with the calcium carbonate plus the 2 hydrogen ions, reacts to form carbon dioxide gas and water liquid. Oh, and the calcium ions, oops, I almost forgot that part. That part's important. Okay, so we should be including states, aqueous and solid, and there is your net ionic equation. Okay, now a student performs an investigation to study factors that affect the rate of the reaction. In each trial, the student combines 50 milliliters of HCl at 21.2 degrees Celsius with 1 gram of calcium carbonate, measures the time. And then, so it looks like the difference here is there's 2 different concentrations and 3 different surface areas, okay, or particle sizes. Student correctly identifies that trial 5 is inconsistent. Explain why the student's claim is correct. So trial 5 here, we would expect that small chunks would go faster than large chunks, and it doesn't here. It takes more time, so it's slower. So small chunks have larger surface areas, so there can be more collisions. So you would say that this one does not follow the correct pattern for reaction time. Now for part C, it says, based on conditions and collisions that occur, please explain the reason for the difference in the reaction times for trial 2 and trial 3. So our concentrations are the same, so we can't look at concentration. What's different here is the small chunks versus the large chunks. So really, C is very, very similar to B. small chunks will have more surface area. And because it has more surface area, it allows for more frequent collisions between particles, which increases the rate of the reaction and gives it a lower time. And for part D, the student claims that the reaction is zero order with respect to HCl. Do you agree or disagree? So a zero order reaction is just rate equals K. To compare, a first order reaction is rate equals K times the concentration of your reactant, which in this case would be HCl. So essentially a zero order reaction will have the same rate regardless of the concentration. So if you look at the data table, and let's compare like the two with fine powder. They have the same particle size but different concentrations, and the time of the reaction is different. So you should have used like a specific data point. It didn't matter which ones you were comparing per se. You could have used the fine powder or the large chunks. You could have even used the small chunks, but you wanted to make sure that you picked specific data and said that yes, changing the concentration does affect the rate, therefore it cannot be a zero order reaction, and you should disagree. Okay, so the HCl was excess in all of the trials. Determine the molarity of HCl in the beaker after the reaction is complete in trial 2. Assume that the volume of the mixture remains constant at 50 milliliters throughout the trial. So we had 1 gram of calcium carbonate being mixed with the 50 milliliters, and in trial 2, that was 1 molar HCl. Let's go ahead and find out how much of the HCl actually reacted. We have the 1 gram of the calcium carbonate. They gave us the molar mass, which was nice. But we know that for every 1 calcium carbonate that reacted, used up 2 of the HCl. So we got 0.0200 moles of our HCl that reacted. Well, I'm going to change milliliters to liters. 0.0500 liters times the 1 molar gives us 0.0500 moles of HCl that we had to begin with. So we can then just subtract how much reacted to get that there are 0.0300 moles remaining after the whole reaction is done. And so that's the moles, but it wants us to know the molarity. So let's go ahead and change that back to molarity. So moles divided by the 0.05 liters gives us a 0.600 molar solution at the end. Okay, so now we're repeating the reaction. We're repeating trial 1 by mixing 50 milliliters of the 1 molar with 1 gram of calcium carbonate using a calorimeter this time. Records the temperature every 20 seconds. Is the reaction endothermic or exothermic? And justify your answer. So the temperature is increasing. Not a lot, but it is increasing. And so the thermometer can only measure the surroundings. And so because the surroundings are increasing in heat, the system must be losing heat. So it must be an exothermic reaction. And now, based on the experimental data, the mass is 51 grams and the specific heat of the reaction mixture is 4 joules per gram Celsius. Calculate the magnitude of the heat transfer, so Q equals mc delta T. And our mass is the 51 grams. The specific heat is 4. We just need to actually find the change in temperature, which for this reaction, we need to take that final temperature that they gave us, the 21.90, and subtract out the starting temperature, and we get 0.70. And plug that in for delta T, we get Q equals 140 joules. for this process. Now for part II, we want to find the enthalpy of reaction in kilojoules per mole reaction, and we want to include the algebraic sign. So they kind of led us to this question. They told us to find out if it was endo or exothermic. We already said it was exothermic, so it needs to be negative. But from here, we need to go ahead and convert joules to kilojoules. So that will be 0.140 kilojoules. Okay, and then we used that 1 gram of calcium carbonate, which we already know is our limiting reactant. They told us that earlier on, that the HCl was excess. So grams per mole, and that gives us 0.0100 moles. And so then I can divide my kilojoules divided by the moles. And that will give me my overall heat, or enthalpy is negative 14 kilojoules per mole. And remember that negative sign is because we've determined that it was exothermic. Question 4 is the first of 4 short free response questions, and each of them are worth 4 points. Okay, so we're making a buffer with our weak base and our conjugate acid. I always like to annotate the questions like that. The student uses 25 milliliters of 0.1 molar of our weak base, which contains this many moles of our weak base. They didn't need to give you that. You could find that using the volume and the molarity. But anyway, to make the buffer. So calculate the mass of this stuff that you have to make this many moles of the CH3NH3Cl. And the reason we're looking for this many moles is because we want equal molar amounts. This is a kind of strangely worded question, but anyway. So we want to do that to 250 moles, and then I need to use the molar mass of CH3NH3Cl. So use your periodic table, find the molar mass, and you should get 67.5 grams per mole. And so when you multiply, you get 0.169 grams of the CH3NH3Cl, which is our conjugate acid. Okay, so we have a bunch of materials and equipment. Following table contains a partial procedure. Fill in steps 1 and 4 to complete the procedure using only materials and equipment selected. All right. So we just found that we needed 0.169 grams of the CH3NH3Cl. So you want to use an electronic balance, weighing paper, probably a spatula, to weigh out 0.169 grams of the solid CH3NH3Cl. That's your step 1. Weigh out the correct amount that we calculated from part A. Step 2, you're going to place that in a beaker, clean the burette and rinse it with distilled water, step 3. So they must want us to use the burette for their next step. I'll use green. So our next step, we want to use the burette. You are going to rinse with the 0.1 molar CH3NH2, and then you will fill the burette with the 0.1 molar CH3NH2. You want to make sure that there's no more excess water like left over in your burette. So you want to rinse it with the titrant first. I say titrant, but rinse it with the substance that you're trying to dispense first, and then fill it with that substance to make sure it's really, really accurate. And that should be it, because then step 5 says to use the burette to add 25 milliliters to the beaker. And so you are done there with step 1 and step 2. Okay, so now they give us the Kb for that weak base, and the pH of the buffer is 10.64. Okay, the student prepares a second buffer solution. We use 25 milliliters of 0.05 molar CH3NH2 instead of 25 milliliters of 0.1 molar CH3NH2. Okay, so notice that the molarity is now half. So our weak base has half the molarity. Okay, And then half the mass, so our conjugate acid has half of the mass of the CH3NH3Cl. Is the pH of the second buffer greater than, less than, or equal to the pH of the first buffer? And justify your answer. It's going to be the same, equal to. So if I am decreasing both of those things by half, and if I half the molarity, I will also have half of the moles. If I half the grams, but it's the same substance, I'm going to have half the moles. So it will still be equal moles of those two things, just half. All right, so the mole ratio is still the same. And then if you want to, you can explain using Hess'S equation, pH equals pKa plus the log of the weak base over the conjugate acid there. And so you still have the same ratio, which is 1 because they're equal. So your pH is still equal to the pKa. Question 5 is the next of the short free response questions. Okay, we have hydrogen chloride gas, really. It's stored in a rigid 6-liter container at 7.45 atm and 296 Kelvin. Calculate the moles. Pivnert. Pressure 7.45. Volume is 6. Gas constant. And our temperature. Very straightforward. Solve for moles. And you get 1.84 moles of that HCl. Now we have a rigid 6-liter container. It's cooled to a temperature of 271. Calculate the new pressure. You could do this one of two ways. You could use the combined gas law, or you could assume that since you're cooling it, you still have the same number of moles. All right. So I don't know pressure. Volume is 6. N is the same. R is the same. Temperature is now at 271. And if you solve for the new pressure, you get 6.82 atm. So that's using Pivnert. Now if you use the P1 over T1 equals P2 over T2, that's fine too. You'll get the same answer. But this equation is not on the formula sheet, whereas Pivnert is. Now when HCl ionizes an aqueous solution, chloride ions are formed. Draw 3 water molecules with proper orientation. So we want to draw them with the hydrogen atoms close to the chlorine because the hydrogen side of the water molecule is slightly positive and the oxygen side is slightly negative. Now for part C, they give us the Ka values for 3 different acids. Whenever I see acids, I like to label them. So this I know is a weak acid, this is a strong acid, strong acid. Now if you couldn't remember that, they actually gave you the Ka values. Do you see how large these two numbers are? That's your clue that those are strong acids. But you should have those strong acids memorized. Now, following particulate diagram represents one of the acids. Water molecules have been emitted. Which acid is represented? Notice how most of those have the acid still stuck together. That means only some of it ionized into those separate ions. So that means it must be the HNO2 because that's the only weak acid and it has the smallest Ka value. I would say that you definitely have to mention the Ka value because of the way the question is worded. It's just using the information in the table. So saying that it has the smallest Ka value, so only some of it ionizes. Or has a Ka significantly less than 1, something like that. Would give you the answer there. Continuing on with question 6 as our next short free response question. Okay, so we need to list the types of intermolecular forces, Hbr. Everything has London dispersion forces. They're both polar molecules. They have an uneven distribution of electrons in the atom or in the molecule, so it definitely has dipole-dipole for both of them. But HF also has hydrogen bonding because of that fluorine. Now, they give us the heat of vaporization for each liquid. That's the energy required to turn it from a liquid to a gas. Explain why the heat of vaporization for HF is greater. Even if you didn't know what heat of vaporization was, you could still assume that, it's because hydrogen bonding is stronger than the LDF and the dipole-dipole forces in the HBr. So based on the stronger hydrogen bonding in HF, that's why it takes more energy to turn it into a gas. Now we want to calculate the amount of thermal energy in kilojoules required to vaporize the 6.85 grams of HF. Pretty much anytime you see grams, you should change it to moles. So let's use the molar mass of HF, which is just about 20 grams per mole. And so when you divide there, you get 0.343 moles of HF. And then you can multiply by the 25.2 kilojoules per mole. That way the moles cancel. And so then you get the final kilojoules is 8.63 required to vaporize that much HF. Okay, so we want to look at the difference between the Hbr bond length and the HF bond length. And we want to look at the arrangement of electrons. Bromine has 4 energy levels for its electrons. Fluorine only has 2 energy levels. The larger number of energy levels means that its valence shell is further from the nucleus, so it has a greater atomic radius, which increases the bond length. Whereas fluorine has a much smaller radius because of those fewer energy levels, and therefore will have a smaller bond length with the hydrogen. And question 7 is the last of the short free response questions and the last of all of the questions on the AP exam. Now for this one, they give us the solubility equation and the KSP expression, which is very nice. But then they give you this drawing, and notice how the hydroxides are all separated from the strontium ions. Water molecules are intentionally omitted. Identify the error. So because it is a only partially soluble salt, even without knowing the value of KSP, we know that some of them will still be solid particles that are bound together. So the drawing should have had some of the strontium and hydroxides still together and not completely ionized. Okay, the student prepares a saturated solution by adding excess of the strontium hydroxide to distilled water and stirring, and then the student determines that the strontium ion concentration is 0.043. Calculate the value of the OH. To do this, all we needed to use was that balanced chemical equation. We know that if we have 0.043 molar for the strontium, there's 1 strontium ion for every 2 hydroxide ions. It's going to be twice similarity, so 0.086 molar for the hydroxide. And we know this because you're just starting out with solid strontium hydroxide. And so we know that it dissolves within that ratio, so that's why I can just skip straight to the stoichiometry for that 2-to-1 ratio. Now we need to calculate the KSP value, so I want to use my KSP expression that they gave us. And there's no reactants because they're solid, so I just want to plug in the strontium that they gave us here, the 0.043, and then we'll plug in the hydroxide that we found, and that's squared. And then you can solve for the KSP value, which is 3.2 times 10 to the -4th. Now in this case, we're going to prepare strontium hydroxide in aqueous strontium nitrate instead. I'm writing out the balanced equation here again. In aqueous 0.1 molar strontium nitrate instead of water, will the value of hydroxide be greater than, less than, or equal to the value in the first solution? So if I have the strontium nitrate that is completely soluble, that increases the number of ions of strontium in the solution. And according to Le Chatelier's principle, it's going to cause the reaction to shift in the direction of the reactants to use up the excess strontium. So I'm going to produce more solid strontium hydroxide, but that, as a result, will decrease the amount of hydroxide ions present in the solution. So the hydroxide ions will be less than the first. And then you could call this the common ion effect, which is what it is, or you could use Le Chatelier's principle, like I did to begin with here. You could also use Q and compare Q to KSP. I think any of those would be acceptable here.